lesson 3A, the application lesson. So again, exponential function, we know exponential function is a to the bx. We're familiar with that. We also know that when your b is bigger than 1, it's growth. When your b is between 0 and 1, it's decay. It's going downwards. Okay, you're halving something. Okay, you're quartering something. All that stuff is decay. All right. So write an equation using y equals ab to the x. There are many applications for exponential functions in real life. We just did one. We just did this is principal would be your A. Your B was always growth for interest on those, right? Because we were adding money to our stuff, so that was growth. And then to the n. Okay. All right, so let's go and look at this first example. Essentially, the idea for this lesson, if you didn't see, is growth and decay, which you kind of already know a little bit about. In 2012, the university population of a country was 160,000 and was increasing at an annual rate of 4.5%. If the function representing the population of the form y equals a to the bx, state the values for a and b. So in this case, your a is the starting amount, so that's your 160,000 people. Your b is the growth. It is growing, so you add 1.045 to the x, would be your y equals abx form. That'll be your population. Oops, I kind of wrote, sorry. This is for part B. They just wanted us to say what A is. A is 160. B is 1.045. So B is the equation. And then C, determine the population in the year 2015. So that's going to be in 3 years. So we'll put a 3 in for X. So 160,000 times 1.045 to the 3. Calculate. You get 182,587. Okay. And if it says the population continues to grow at this rate, determine the number of years to the nearest year for the population to double from 2012 size. So we want to double. So this is where we're going to go and do that work. We go 320,000 would be double. Okay, equals 160,000. And then it's going to be the work we already did in the previous lesson. So we're going to figure out how long. Sorry, it's an x there. So you divide the 160, so that's 2. And then we'll convert to exponential or logarithmic form, right? So 2 equals 1.045 to the x. And so that's what it is, right? Log base 1.045 of 2 equals x. And now we could do change of base. Okay, I won't write the change of base. We've seen that enough. It's log 2 over log 1.045. You're going to get 15.747. And so the nearest year, you'd round up to 16 years. So in 16 years, it will be doubled. Always round up when you're talking about stuff like this.
So what if it's like 15.2?
Still going to round up. Because if you say 15, it's not doubled there because you're going back. Yep, good question. All right. Okay, let's keep on going here. Any questions? I think this stuff's pretty, you kind of know this stuff. All right, so let's look at example 2 here. All right, number of fish in the lake is decreasing by 5% each year as a result of overfishing. Okay, if a number of fish present in an exponential function of time, state the base of the exponential function. So the base of it, that means your b. What's your b? If it's decreasing 5%. What'd you say? No. No. Decreasing by 5%. So from 1, it decreased by 5%. So if you put 0.05, that's 95% decrease from 1. You're thinking about from 1. Okay, so it's 0.95 there. So how you do that, if it's decreasing, you just minus the percent. You're going to get 0.95. Okay? The common mistake is to put 0.05 and you're losing a lot of fish that way. Okay? Write equation represent the number of fish after t years. So then we're going to have number of fish. We don't know how many we started with, so we use n naught for how many we started with. It'd be 0.95 to the t. There were 2,500 fish present in 2012. How many would you expect to be present in 2017? So now we put 2,500 there. And we do it for 5 years. And so now we calculate. After 5 years, it'd be from 2,500 to 1934. So almost 600 fish would be lost from the overfishing. Yeah, that's a lot of the reason why there is, a lot of departments like Parks and Rec and the people that keep track of the fish and wildlife and all that stuff. They're counting all that stuff is to see how that stuff's going. Even in hunting, they do that. That's what kind of determines who gets tagged and who doesn't, because they're saying, okay, we can't give out what we gave last year because we're getting a less draw. Then we're seeing less deer or less elk or whatever the hunting's for. So they use a lot of this kind of stuff to determine that. How many years to the nearest tenth? So now we're going to solve the years thing. So we know we're going to be using our log stuff again. So how many years to the nearest tenth would it take for fish population to reduce to half? So for half, we're going from our 2,500 to 1,250. So from 1,250 to 2,500, 1.0, nope, not 1.0, we're not growing, 0.95, sorry. So we got 0.95 to the t. And so we know we divide the 2,500 over, it's going to give me 1/2 or 0.5. And now we're ready to write that in exponential. Log base 0.95 of the 0.5 equals t. Now you do your change of base. And you're going to get 13.51. Okay, so if you want to round up to a full year, it'd be 14 years it would take for you to lose more than half. If you want to be more specific, about 13.5. Okay. All right, example 3. The intensity I0 of a light source reduced to I after passing through d meters of fog according to the formula I equals I0 E. So this is a natural number, E. Remember, E is a value. Don't forget. But remember, if we're looking at E, if we're going to do logarithm stuff, we're going to think about ln. Okay, just heads up. Negative 0.12 d. At what distance to the nearest hundredth of a meter will the intensity be reduced to 1/4 of its original value? So the thing is, this is actually like a kind of a good diploma/SAT question because it's not giving you a lot of just straight numbers. It's making you have to figure it out. But if it says 1/4 of the value, do we need to know these two numbers? Because what's happened every time? Our first step, we divide, when it said half, we divide over, and then we got half, right? So what you're going to do is you're going to say 1/4 equals, these are gone, e to the negative 0.12 d. That's where you're at. So if we don't know what the starting amount is or what it's going to be if it's 1/4 of it, but we do know when I divide this over, that value will be 1/4. That's what's kept happening, right? We got 1/2 before, and so just knowing that operation is going to happen, that's where you'll be. Okay? You don't get that? Okay, so let's go back to the previous one real quick. Okay, so we talked about over here. It says, when would you expect there to be half as much, right? Where was that? Right here, D. So half as much. So half as much was 1,250, remember? And then 2,500 is how much we started with. So whatever, this stuff here, we don't need this right now. When you divide over, that first step you do, this becomes that 1/2 we're talking about. And so we don't need numbers. If it tells us it's going to be 1/4, we don't need to know what those are. We know when I divide this over, it's going to be 1/4. Okay, so it's going to be 1/4 equals the E. So it's just like pretty much you're taking a shortcut. We don't need the numbers. Now here, what's helpful here is that we do want to write this. You could write in log form, but log with a base of E is ln. So this is actually easier to ln both sides. Okay, so we would just write this, ln of 1/4 equals ln of e to negative 0.12d. Now, why is that helpful? Because this is a value, this cancels, and this drops down. So you essentially know ln of 1/4 equals negative 0.12d. And we just have to divide by negative 0.012. Remember, why does ln e cancel? Because ln is log base e. Okay, that's in your notes from our logarithm section. This right here, remember, log base e of e, well, you don't log base of a number, it's the same thing as 1. So that's just be 1. Same rule, the power law says I can drop this in front. If I drop this in front and cancel this, that's all I have left. So your last step is just to do this. Like that. Oops. Move the 0 on accident. Like that. So when you calculate that, you're going to get 11.552. And that's going to be meters. So the question says, would you answer? You said at what distance? So at 11.5 meters, the intensity would be reduced by 1/4. Okay. So this is just talking about light going through fog. So the farther you're back in the fog, the dimmer your light is. The closer you get, the brighter your light is. But obviously your light is being affected by the fog. And so it's saying at 11.5 meters, your intensity will be decreased by 1/4. Okay? All right. Let's just keep going. We're doing good. All right, half-lives. This is, you probably talked about this in science or biology a little bit sometimes. You have radioactive substance decaying. They use half-life in terms of it's just always halving its life, but it's not always completely gone because it's still a little bit there. But essentially, we have let A represent the amount of radioactive substance present at a time t, and A naught represent the amount present initially. For some base B, we can exponentially function of A equals A naught B to the t. So that's just normal. This is our normal A. But complete the following to determine the base in terms of the half-life. So when T is H, only half the substance would be radioactive. So essentially, we need to put a half in front of the growth of that radioactive material. That's what we have to do. And so now we're solving for B. It's just kind of working out the formula. So if you're not following right now, that's okay. But the important part is this piece. Okay, so you have your initial half. So 1/2 is your B, which means decay, right? Because you're half-lifing, so it's getting smaller or losing using its life, exactly. 1/h to the t. And then they just multiply that t in here because this is power to power. So multiply that there, so it's t/h. Okay. All right. Conversely, the same thing for doubling time. So if it doubles, it'd be the same exact formula, but with a 2 here. Okay, so you got doubling time, half-life. 2 versus a half. Okay, well, let's just use these now. This is the breakdown of it. C, a constant. That's what you're going to be looking at in terms of your base. So that's your C. Oh, so C is going to be the constant of 2 for doubling, tripling, or half-life. So C is the whatever they're asking you to do. So if it's half-life, it's 1/2. If you're doubling, it's 2. If it's 3 for tripling. Okay. A naught's the initial amount. A is the amount of time. So the answer will give you the amount of time. T is time. P is the period of time for doubling, tripling, or halving. So that's how long we're doing it. 20 years, 15, whatever. So like if it says it triples every 3 years, let's just say, oh, let's not do that. So it triples every 2 years. Then you would put right there 3, but for period it'd be 1/2. Because it doesn't triple until 2 years. Yeah. Okay, so let's try one. Patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. 24 hours later, the sample was recounted and was found to contain 8,012 cells. Find the doubling period of bacteria to which the nearest tenth of an hour. So we're trying to figure out how fast these are doubling. So we know she currently has, so our A is 8012. Nope, we know it says doubling, so we know C's double. We're trying to figure out how long. Or sorry, no, yeah, the period, doubling period. So we're trying to figure out when does it double. Okay, so we know that the starting amount was 387. We know that C is doubling because they said doubling in the problem. T is 24 hours because that's how long it took. And P is what we're solving for, the period. We're trying to figure out how often is it doubling. So if we set this up, remember, this is the original. Like that. A naught C to the T over P. What's wrong? Is it crazy form? Yeah. More and more letters. So T, we're doing 24. Just know we're working in hours. So that's how we plug everything in, and see we're solving for P. No, the formula is time over P. Yeah. And so now we're going to just do our normal stuff. We're going to divide by 387. Okay, we'll leave that like it is because it's going to be a decimal. But remember, that means that we're going to go 2 to the 24 over P. And so what we're going to do is we're going to go log base 2 of 8012 over 387 equals 24 over P. And so what we're going to do is we're going to want to flip that, right? Do you guys see what's going to happen here essentially? Essentially, that's what's going to happen. Do you remember this from your like Math 10? Or Math 9 actually does quite a bit. We're trying to solve for P, right? So I'm going to times P over here, and this is going to go underneath. These are going to switch spots essentially. This value is going to switch spots with the P. So it's going to be 24 divided by this whole thing is your answer. Okay? 24 divided by this whole thing will be your answer. Essentially, these switch spots. If you don't know why, because we're going to times the P over, and we're going to divide this guy over. So that's what's going to happen when you switch. So it's going to be P equals, when you do that calculation of 24 over log base 2 of 8012 over 387, you get 5.489. What that means is, what was our time that we were using? What unit? No, our time unit. Hours. That means it doubles every 5.5 hours. What's that? Yeah. Okay. Yeah, and that's what you put in your calculator. Yeah. Okay, sorry. If you want me to put up there, you put this in your calculator. So you do 24 over log base. Yeah, you're going to have to do it kind of tricky. 8012 over 387 has to be on top. And then this is over log of 2, right, for your change of base? Yeah. Yeah, you get the formula test. All right, we're still clicking along. Let's just keep going. We're almost done. We have 2 more examples to solve. Is that fine? 2 more examples. All right. In April of 1986, the nuclear accident in Chernobyl, right? Yeah. Okay. Chernobyl. Yeah. I said it wrong before. Yeah. Looks like Cheryl. Okay. Contaminated the atmosphere with quantities of radioactive iodine, 131. Its half-life of the radioactive iodine, 131, is 8.1 days. Determine the number of days to the nearest day it took for the level of radiation to reduce to 2% of the original level. A lot of numbers here. Okay, but this is interesting. I think it's interesting. Okay, so we want, again, what do we want our A to be? So we don't know how much radioactive material, right? but we know that we want it to be 2% left. Like how much for it to be 2%? Okay, or reduce 2%, excuse me. And we know that we're starting out with, then, how much do we start out with in terms of percent? 100. 100% is there. Okay, we know it's a half-life. Yep, we don't know T, but we know the period is 8.1. And that's in days. Good work. So what can be helpful from here is that we're trying to get, if you're confused on this, that's fine. But essentially, if we want to move A naught over, 2 over 100 is 0.02, right? So we're essentially going to have 0.02 right on this side, the left side. Because I'm going to divide the 2 over to the 100. And so then I'm just kind of making it a little bit shorter. So it's going to be 1/2 T over 8.1. So now we're ready. All right, so we're going to go log base 1/2 of 0.02 equals T over 8.1. And so we're going to times that log by 8.1. So in your calculator, it would be this. Log of 0.02 over log of 1/2 times 8.1. Yep, always, yeah, change the base, yeah. To calculate these. And that gets you 45.7. So we're going to say 46 days for a 2% radiation to decrease by 2% of the original level. Okay, last one. Thanks for hanging in. Good job. All right. Radioactive isotope has a half-life of 7 years. Okay. Use a formula right here with C of 1/2. Determine how much of the isotope must initially be present to decay 60 grams in 14 years. Okay, so we know that means that we're trying to figure out when's it going to decrease by 60. We don't know, yeah, see, it says how much is initially present. So what's that mean? We don't know this. We don't know A naught. So A naught's what we're solving for. We know our C's 1/2. And we know T is 14. And we know the period is 7. Because his half-life is 7 years. So we have everything but the initial amount present. So when we set this up, it's like this. 60 equals A naught 1/2. 14 over 7, I'm just going to write a 2. Is that okay? Yep. Okay, 14 over 7. Okay, so what do we do now? So people get like, they forget. Yeah, just square it. We can square this. And then we can divide it. Okay? Or since you're going to times, right? 1/2 squared is 1/4. How do you get rid of 1/4? You times by 4. So A naught is 240. Yeah. Write an equivalent formula with C equaling 2, which would solve the problem in A. So let's just say it's not half-life, it's doubling. So that means it would be 60 equals A naught 2 squared. But instead of 2 but if we're not just changing the problem, excuse me, they don't want to make doubling. They want you to write the 2, so what would you change? How do I write 1/2 as 2? Like a base of 2. Negative, and so we'd call it -2. They're just showing you use your exponent skills there.
Why negative?
Because we're changing 1/2 to 2, so we flip. So the flipping changes your exponent to negative, right? they're asking you to write with a base of 2 instead of 1/2.
Oh, I thought they just meant like.
In your class.
Yeah. Right. And sorry, let's finish this here real quick. Last one. It says, in the particular example, explain how the solution to the problem could be found without using any formula. Without using any formula, essentially is just 14 years as a half-life. So I'll just talk about it. So the initial amount of 1/2, then another half would give you 1/4. So it's half of a half. Okay, because we're trying to figure out how long. And so if you think about if it's 1/4, okay, 60 is 1/4 of the initial. So then how do I find the initial? Times by 4. So you're doing 2 periods of a half-life. So 1/2, 1/2, or 1/4. You would times that by 4 to get 240. So I'm just kind of talking it out loud. Okay, all right, sticking that up.